The fast Fourier transform, or FFT, is actually not yet another Fourier representation, but it's an algorithm. It's a numerically efficient way of calculating the DFT. It's had a profound influence on the development of signal processing as a discipline. It was originally developed by Gauss in 1805, but really not recognized until more modern times that he contributed to it. In 1965, Cooley and Tukey published a paper on the fast Fourier transform, an efficient way to do it, and of course the time was ripe then because digital computers were growing and there was a need for faster and faster data analysis. So we're going to begin by reminding ourselves about the DFT. So the DFT is given by this expression that I've put up on the slide here, that x of k, frequency domain coefficient, is a sum over time from little n to 0 to n minus 1 of x of n times these complex exponentials, these complex sinusoids. We have to do this for k equals 0, 1 up to n minus 1. So if we consider how much computation is involved here, we have n complex multiplies and n minus 1 complex adds to get each x of k. I have to multiply x of n times e to the minus j 2 pi k over cap n times little n, and I'm assuming these numbers are pre-computed and are stored in the computer, so I just have to do a multiplication. I have to do that capital N times because there's n terms in the sum, and then add those up. So if I consider the capital N values of k that I have to compute, I have to do each of these computations for each k, so that gives us a total of n squared, and I'll write order n squared. That's what this means. We're not going to worry too much about the constants, but it's order n squared computations to directly compute the DFT. Now we'll see in a few minutes that the FFT reduces this from order n squared to order n log 2n. Now you might say that, well, n squared, n log 2n is not a big difference, but it turns out it is when n gets very large. So you have a little table, some different values for n, and the difference between n squared and n log 2n. So when we're at 1,000, n squared is 10 to the 6th, and n log 2n is 10 to the 4th. So the FFT provides roughly a savings of 100. But as you increase n, here we're at 10 to the 6th, then the n squared requires 10 to the 12th operations, and we've got 20 times 10 to the 6th operations for the FFT. Well, if we go even bigger, say 10 to the 9th, then we end up with n squared being 10 to the 18th, and n log 2n is 30 times 10 to the 9th. Let's suppose that each operation took a nanosecond, each multiply that we're counting here. Well, 10 to the 18th nanoseconds turns out to be on the order of 31.2 years. In contrast, if I have the FFT algorithm and I can cut this to 30 times 10 to the 9th, it turns out that that's on the order of 30 seconds if it takes 1 nanosecond per operation, per multiply and add. So you can see that we've got a dramatic reduction in the time that it takes to do this computation. So the FFT algorithm, basically it exploits the special properties of the complex exponential e to the minus j 2 pi divided by cap n times k times little n. And it's conventional to define a symbol w sub n to represent e to the minus j 2 pi over n. And with this symbol, we can write two of the important properties as follows. We have the complex conjugate symmetry, which says that if I look at time cap n minus n, w sub n k raised to that power is actually the same as w sub n to the minus kn power, and that's the same as w sub n to the plus kn conjugate. And it's easy to see here that w sub n to the kn is exactly equal to, well, let's write it out. It's e to the minus j 2 pi times k, because the n's cancel and the 2 pi over n cancels with the n here, and this becomes exactly 1. The second property that plays an important role is periodicity. this W sub n is periodic in both k and little n, with period capital N. So if I add capital N to little n, I get the exact same result as I started from. And if I add capital N to k, I also get the same result. And this basically also follows from this property that wk to the cap n is exactly equal to 1. And the other thing that we do is we break up the big DFT into smaller ones, and that turns out to save us some computation. To illustrate that, we're going to look at the decimation in time FFT algorithm. This is one of many variants of FFT that have been proposed. We're going to assume that capital N is 2 raised to a power of m. So it's something like 256, 512, 1024, 2048, 4096. Those are all values of 2 raised to some power. Now there are other FFT algorithms that apply to more prime type factorizations of n. We're not going to look at those. We're just going to get the idea of how these algorithms work with this specific case. And so the idea is to separate your data into even and odd indexed subsequences. So here I've written out the DFT where I've replaced the e to the minus j 2 pi over n times k times little lowercase n, replace that with my w notation. So this is my DFT, and I'm going to break that up into a sum of terms involving even indices for n and a sum of terms involving odd indices for n. Now I can write an even index as n equals 2 times r, where r goes 0, 1, up to n over 2 minus 1. And remember, n is a power of 2, so n over 2 is an integer. And I can write my odd indices as n equals 2 times r plus 1, where again r ranges over this interval. Thus, x of k, my DFT coefficient, can be expressed as a sum over r, where I have, in place of n, for the even indices, I have x of 2r. And then, of course, I'm going to replace n up here with 2r. And then for the odd indices, I have x of 2r plus 1, and then w sub n 2r plus 1 times k. What we're going to do is factor out the term of w here that doesn't depend on r. So I have w sub n times 1 times k. So we'll pull that out front of the sum. And then we'll also recognize that w sub n to the k times 2 times r is just w sub n squared, whole thing raised to the kr power. Trick here now is to recognize that wn squared is the same as w sub n over 2, because I can take the 2 from the numerator here, put it in the denominator, and divide n by it, have the same expression, but that's w sub n over 2. So this allows me to write this DFT as a sum of x of 2r, so I'm just picking out even values of the sequence, times w sub n over 2 to the kr, and then we have this factor that we had pulled out earlier, times the sum r equals 0 to n over 2 minus 1 of x of 2r plus 1, the odd subsequence, and then w sub n over 2 raised to the kr power. Well, looking at these expressions, we recognize that the first summation here is an n over 2 point DFT associated with the even samples of x. We're going to call that n over 2 point DFT, those coefficients, x sub e of k. Then we're going to look at this other sum here and say, well, that's just an n over 2 point DFT of the odd samples of the input signal. And we'll call that DFT x sub 0 of k for odd. So our DFT can be written as a sum involving two n over 2 point DFTs, one for the even indexed time values, and then the other involving the odd indexed time values, and we have this factor w sub n to the k. So we have a sum of two n over 2 point DFTs that we can use to get our n point DFT. So here we've sketched a block diagram of this splitting process for the case when the order capital N is equal to 8. So in the upper portion here, I've gathered the even samples, x0, x2, x4, and x6, and those go through an n over 2 point DFT, which in this case would be a 4-point DFT, to produce the DFT coefficients associated with those even index terms. And then down below we have the odd index terms, x1 through x7, and those go through another n over 2 point DFT to produce the DFT coefficients associated with the odd index terms. And this next stage does the combination of the even indexed and the odd indexed DFT coefficients in order to get the DFT coefficients of the entire sequence. So you can see from this block diagram that we're going to take 1 times xe of 0, and then we're going to add to that w8 raised to the 0 power times xo of 0, and that'll give us x of 0. And similarly, we're going to take 1 times xe of 1, and we'll add to that w8 to the first power times xo of 1, and that'll give us x of 1. And this is our equation for combining the even and odd DFT coefficients to get the overall DFT. And similarly then, down to the bottom here, we have 1 times xe of 3 plus w raised to the 7th power sub 8 times x0 of 3, and that gives us x of 7. If we look at the computational count of doing this kind of splitting, we see that we have two n over 2 point DFTs, and if we implement those just directly according to the equation, we're going to have n over 2 multiplications squared, and we have 2 of those. And then on this right hand side of the diagram, we have multiplies by these w sub 8's raised to various powers. And we can pre-compute those w terms, so in each of these cases we just multiply by this number, so there's a total of n multiplies because there's n different outputs here. When you combine these together, you see that you have n squared over 2 plus n multiplies. And that's compared to starting with n squared multiplies. So if n is large, we've cut the number of multiplications required in half by splitting the sequence up into even and odd index terms and doing a smaller DFT of each of those and combining it later. Well, this splitting saved us some computation. So why not continue this process and take each of those n over 2 point DFTs and replace them by two n over 4 point DFTs. So we can continue splitting. Remember that n is a power of 2, so we can go from n over 2 to n over 4 and keep on going, and we get to n over 2 to the p minus 1, and finally n over 2 to the p, where p is log 2 of n. And n divided by 2 to the log 2 of n gives us exactly 1. So that's the maximum number of times that we can split as p, and it turns out that we end up with a 1-point DFT at the end. So if we count the cost of doing this, we started off with one level of splitting. We had n over 2, and there were 2 of those, so we had 2 times n over 2 quantity squared plus n computations, which we saw was n squared over 2 plus n. Well, if we go to replacing these n over 2 point DFTs by 2 n over 4 point DFTs, then that's going to give me, so I'm going to have 2 times n over 4 squared plus n over 2, replacing the n over 2 squared plus n. And that turns out to be n squared over 4 plus 2n. You can do n over 8, and if you follow through the logic again of now having 2 n over 8 point DFTs replacing each of the n over 4 point DFTs, you end up with n squared over 8 plus 3n. So if you continue this p times, where again p is equal to log 2 of n, then it turns out that you end up with a 1-point DFT, and if you carry on this pattern, I have n squared divided by 2 to the p plus p times n. which comes out to n squared plus n log 2n. And n squared over n is just going to be n here. And for capital N large enough, this term dominates n, and we say that the computation is order n log 2 of n, if n is large. So to get a feeling for what this algorithm looks like, we've drawn what's called a signal flow graph here, a graphical representation for the FFT algorithm in the specific case where n is equal to 8, and that's 2 to the third, or p is equal to 3. So we should have 3 stages here, and indeed we do. We have this first stage, a second stage, and then the final output stage. What happens when you take this splitting of even and odd sequences and then you split those into even and odd, you get an interesting order. So we have x0, x4, x2, x6, and then x1, 5, 3, and 7 coming in, and each of those goes through one of these operations where we're combining with other results from a lower DFT, multiplying by the appropriate W coefficient. And then the second stage, again, you've got the appropriate powers of W sub 8, and then finally in the third stage you have yet another set of powers of W sub 8. And a lot of these coefficients are 1. It turns out that some of these are even simpler than it looks because W raised to the 0 power is 1. So there's really no multiply here. W sub 8 raised to the 4th power is actually minus 1. Okay, so some of this first stage here is just adding and subtracting, and then the second stage has some elements that are just simple addition and subtraction as well. Now this order on the input side, it turns out that if you take the index of the value and you represent it in binary, so if I have 8 samples, capital N equals 8, I need 3 bits to represent those. So then a particular index like 0 would be 0, 0, 0, whereas 1 would be 0, 0, 1, and 2 would be 0, 1, 0, and so on. If you take the binary representation for the index and you reverse the bits, then you get the order that things are supposed to be in. So 4 has binary representation 1, 0, 0. Reverse the bits, you get 0, 0, 1. This comes in the first element. 2 has binary representation 0, 1, 0, which when I reverse it stays in the same place, and so on down the line. So actually this is called bit reversal. These are in a bit reversed order for this decimation in time. And then you also notice that throughout this diagram the fundamental computation has this sort of butterfly shape to it, where we're taking 2 terms and we're combining them, and that is indeed known as a butterfly. So the FFT algorithm really improves the speed of the DFT, and particularly when we look at things like doing multidimensional DFTs for images and 3-dimensional objects, it's absolutely critical that we have a fast algorithm if we're going to be able to compute these DFTs on reasonably sized lengths of n. MATLAB relies on it extensively anytime you do a DFT, and there's many variations on the DFT that apply to sequence lengths, for example, that are not powers of 2. They also apply to transforms involving cosines, like the discrete cosine transform. You can do similar kinds of things. So it's a pretty fundamental tool in signal processing.